we're going to go ahead and get started with our webinar today on airflow control devices. My name is Abdul Isi. I'm an engineered technical sales contributor at Antec Controls, and I currently have over 6 years of experience in critical space applications. Airflow control valves are vital in ensuring critical spaces such as healthcare and labs are keeping users and buildings safe by minimizing some of those hazard risks that are associated with these types of applications. So the goal for today's presentation is to introduce the basics of airflow control devices and introduce the differences between flow metering and flow measuring technologies. Airflow control devices such as Venturi valves, high-accuracy terminal units, and VAV boxes will be discussed and compared based on recommendations for applications they are best suited for. The learning objectives for today's webinar include being able to explain the differences between flow measuring and flow metering technology, being able to understand the design considerations when applying these airflow control devices on applications, being able to define speed of response and how they relate to the airflow control device comparisons, and finally, being able to show an understanding of the different airflow control devices and the applications in these different type of critical spaces. So for the agenda for today's webinar, we've already covered the introduction. So we're going to go ahead and get started with the first section, which is airflow control devices. This section will include discussions on airflow metering versus airflow measuring technologies, some design consideration when selecting airflow control devices, and then finally discussing airflow control options. We'll then finish today's webinar by discussing speed of response. We'll do a quick summary, and then we're going to open the floor to some questions. The related standards being covered in today's presentation include ASHRAE 90.1, which covers energy standards for sites and buildings, ASHRAE 110, which is methods of testing performance of laboratory fume hoods, and then ANSI or ASSP Z9.5, which covers laboratory ventilation. So with this, we're going to go ahead and get started with the first section, which is airflow control devices. As mentioned in the introduction, airflow control valves are vital in helping keep users and buildings safe by reducing some of those hazard risks that are associated in those critical space applications. When we talk about airflow control devices, we're broadly going to break these down into three functional categories, which includes our legacy terminal unit, our high accuracy terminal unit, and our Venturi valve. Based out of these three functional categories, they will either fall under either an airflow measuring technology or an airflow metering technology. So with airflow measuring, that's going to fall under our legacy terminal unit and high accuracy terminal unit. And for airflow metering, we're going to have our Venturi valve style technologies. So now what we're going to do here is we're going to try to better define and understand what do we mean when we talk about airflow measuring versus airflow metering. Well, in essence, airflow measuring essentially means our actuator on this airflow device is going to move if there's a change in our airflow target and or a change in our duct pressure. So that actuator will continuously adjust based off of changes if our airflow target changes or if that duct pressure fluctuates. On the opposite end, we have airflow metering technology. So this in essence means our actuator will only move if there's a change in an airflow target, not when there's a change in duct pressure. So if there's any sort of duct fluctuations going on, the actuator isn't required to move. It only moves when there's a change in our airflow target. So let's go ahead and deep dive a little bit more on airflow measuring first. So in functionality, airflow measuring means the ability to measure the actual change in our controlled variable and actuate the control device to bring about the change. So in this sense, our control variable is going to be airflow. We're going to want to be able to measure airflow directly, and we're actuating and bringing about that change utilizing the damper adjustment, so an actuator on that damper. So the actuator on that damper is going to move if there's a change in airflow target and if there's a change in our duct pressure. So as you can see there on the graphic on the right, we have this continuous loop going on. So initially, we're going to first sample the airflow through a sensor. Again, that's directly measuring the airstream. That sensor reading will go back to the controller, which will compare it to the set point. After comparing the live reading to the desired set point, it's going to calculate a potential repositioning for the damper and then adjust that damper accordingly. That loop will continuously go on, and how fast that loop goes or how slow that loop goes, there's a variety of variables available for you to control to set that up. So in functionality, we could also call this an electronically pressure independent air valve. Essentially what this means is we need the electronic components of the sensor, the controller, and the actuator in order to control airflow independent of those duct pressure fluctuations. So the first air valve technology that we're going to cover that falls under this category is our legacy terminal unit. So here with our legacy terminal unit, it's typically going to involve some direct airflow measurement using in-stream flow sensors. In the example we're showing here on the left, it's a legacy terminal unit with a multi-point sensor, but of course there are a variety of sensors that can be used in this sort of air valve technology. In this case, the multi-point sensor is measuring total and static pressure in order to calculate that velocity pressure. Typically, you may see up to a 6-to-1 turndown ratio for legacy terminal units, but advancements to terminal unit technology has led to an increase in the overall turndown ratios available for these valves. This can be done through utilizing maybe more modern controls, higher resolution airflow sensors, and improved actuator technology. Now, typically, we're also going to see straight duct requirements for legacy terminal units. This is typically due to the requirement of measuring velocity pressure to determine airflow. Since velocity pressure can be affected by duct turbulence, being able to have laminar flow through that sensor is ideal for accurate measurement. The next airflow technology we're going to cover is the high accuracy terminal unit. So the high accuracy terminal units can utilize a variety of different airflow measuring technology, similar to what we talked about the legacy terminal unit. But in this example, we're going to show a differential static pressure reading via the inlet and that throat pressure port. So here we're utilizing direct airflow measurement using differential static pressure. Typically, you're going to see up to an 11-to-1 turndown ratio out of these air valve technologies on the high end. Now, this turndown ratio is improved via the mechanical application of the Venturi shape. So here you can see on the left again, we're utilizing a Venturi shape which compresses the available airflow area at the center of the valve. This compression section allows us to amplify the airflow signal being measured, giving us better airflow control at the low ends. Other high accuracy terminal units may use similar Venturi shapes, or they may use some other form of a compression section to achieve similar goals. Lastly, typical high accuracy terminal units will also offer some form of protection from lint, dust, or other contaminants affecting the measuring port. So in this example here, we're utilizing a resistant to contamination based off of the static pressure port design, with those static pressure ports being faced downstream of the airflow direction. We'll talk about that more here in detail. So now that we understand the basics of these two airflow valve technologies, we can now start to cover some of the design consideration that goes into when selecting a valve technology to use. So the first design consideration we're going to cover here is the minimum operating pressure drop. The minimum operating pressure drop is the static pressure drop of a terminal equipment measured at its maximum scheduled airflow rate with the damper blade full open. And typically this will be tested in accordance to ASHRAE 130. So in essence, what we're doing is we're designing a test at the worst potential condition with the damper blade full open to see what's the static pressure requirement at damper blade full open to get us the airflow we need. So in actual application, we may design the operating static pressure to be a little bit higher just to ensure the damper can close off a little bit and we can gain some control at that desired set point. Now, comparing legacy terminal units to high accuracy terminal units, you may see high accuracy terminal units will operate at a higher pressure compared to legacy terminal units, but the higher operating pressure does allow for a higher turndown ratio and improved airflow accuracy across the entire published flow range. So again, this minimum operating pressure table does come from a high accuracy terminal unit. So for example, you can see for an 8-inch size 108, high accuracy terminal unit, we're getting about the 50% flow of 450 at zero point 0.1 inches of static pressure. So, as mentioned earlier, in constant volume or variable volume applications, our airflow measuring technology has to have those electronic components to control airflow independent of those duct pressures. So in this case, we're going to utilize either some sort of sensing measuring element. So for terminal units, we're going to cover the velocity pressure feedback, but of course, there are several different types of measuring elements available that can be applied as well. So for terminal units, you may see a velocity pressure feedback, where this is through either averaging pitot tubes or a crossflow sensor that helps measure and amplify that velocity pressure reading, which is then used to calculate flow. And then for the high accuracy terminal unit, you may see a static pressure feedback. So really the advantage of using a measured static pressure is the removal of velocity pressure from the sensing equation. Since we don't have to rely on velocity pressure to calculate airflow, the risk of turbulence affecting a static pressure reading is a lot lower when compared to a velocity pressure reading. Additionally, high accuracy terminal units are going to have improved accuracy within plus or minus 5% across the entire airflow range. So the next design consideration we're going to cover is contamination resistance. So as mentioned earlier, being able to minimize the risk of sensor fouling during normal operation is important, since these technologies are typically being applied in those critical applications. So contamination resistance will be inherent based off of the valve and sensor design. So ideally, the high accuracy terminal unit that's being selected should be able to measure airflow in a manner that helps minimize the risk of contamination. This reduction, this risk will help reduce lint or other airborne particulates messing with the control accuracy of the valve during that normal operation. So as you can see here, this airflow high accuracy terminal unit utilizes static pressure ports. And again, those measuring static pressure ports are on the back side of the port. So airflow isn't directly facing those static pressure ports. So the next design consideration we're going to cover is fan static reset. So fan static reset is important to help start to apply some of those energy efficient design practices on these critical projects. So ASHRAE 90.1 outlines how this can be achieved. So based off ASHRAE 90.1, it outlines that VAV set point reset. So static pressure set point shall be reset based off of the zone requiring the most pressure. So i.e. the set point is the fan set point is going to be reset to lower until one zone damper on that trunk is nearly open. So to enable fan static reset, control should be able to provide either of the following: being able to either monitor the zone damper position or provide some other indicator of a need of static pressure. So for high accuracy terminal units and legacy terminal units, typically you're going to be monitoring the damper position through that actuator feedback. So the last design consideration we're going to cover is valve material options. So depending on the project application and the expected chemical hazards, the valve material or finish will need to be selected to protect the operation of the valve during its lifetime. So ideally, an analysis should be done to compare the hazard against the selected material or finish to ensure we can be able to understand its performance over its lifetime. So typically for high accuracy terminal units, you're going to see, or legacy terminal units, you're going to see a couple of material options that can include, the basic aluminum style airbox, either a phenolic coated applied to that aluminum body to give some enhanced protection, or fully constructing the valve out of either 304 stainless steel or 316 stainless steel. So that covers everything regarding the airflow measuring technology. So now we're going to go back and now cover the airflow metering technology. So in functionality, what airflow metering means is there's no direct link between the value of our controlled variable and the controller. So in this sense, the value of our controlled variable is airflow directly. So there's no direct airflow measurement happening inside the air valve. We're not directly measuring airflow and controlling based off of that. So there's no feedback from the controller or to the controller on that live actual flow. So instead, what we have here is when there's a change in our airflow target, that is when the actuator is going to move. And then when there's a change in our duct pressure, we're going to see that inside cone spring assembly react to that change. So by being able to split up the adjustment of airflow target to what's happening with duct pressure, our actuator will not only move in when there's that set point change, not when there is that duct pressure fluctuation. So we also call this mechanically pressure independent because in constant volume applications, we no longer require electronic components, i.e. a controller or actuator, to control airflow independent of that duct pressure. Instead, we're going to have a mechanical response, which is that cone spring inside the valve. We'll talk about that very shortly. So here we have that Venturi valve. So the Venturi valve, again, is an airflow metering style technology. As I mentioned, there's no airflow sensor inside the airstream. So the benefit of that is we don't require any straight inlet or outlet duct run requirements because there's no sensor directly inside the airstream calculating and measuring airflow for us. So we can put a 90-degree bend right before and after that valve and still be able to control accurately. So instead, how we get airflow feedback from a Venturi style valve is through electronic or positional flow feedback via a precision potentiometer. So as you mentioned, this airflow technology is mechanically pressure independent because we're utilizing that internal cone spring to mechanically respond to those pressure fluctuations. Now, since there isn't any sensors inside this airstream directly calculating flow, this valve technology will have the highest turn down ratio available, all the way up to 20:1. So we'll first cover, we'll just understand and break down a little bit more in detail what we mean when we talk about mechanical pressure independence. So again, if the airflow out of this air valve is staying constant, the actuator isn't going to move. The actuator in this case is adjusting the positional feedback or the position of where this cone spring assembly sits based off of the center shaft. So when there is a duct pressure fluctuation, we're going to see that cone spring expand and compress in response. So if you have an example here of an air valve trying to control to 500 CFM, as that duct pressure goes from 1 inch of pressure all the way to 3 inches of pressure, the cone spring will instantaneously react to that change and essentially compress in response to that higher pressure, allowing a decreased area that flow can get around that cone, resulting in the same constant flow out of that valve. Now, if the pressure again drops from 3 inches to 1 inch, what we'd expect is that spring will then expand, increasing the available airflow area for flow to get around, resulting in that same constant 500 CFM of flow. So again, this is a purely mechanical response occurring. There's no controls or electronic components telling that spring to accommodate for this pressure change. So with that setting the baseline for us, we're going to go ahead and now cover some design considerations when selecting these airflow metering technologies. So as I mentioned, there is no air relationship between airflow since we're not directly measuring airflow. So since there's no way to correlate the valve's operating pressure to airflow, we need a method of ensuring the valve will operate and control accurately. So for a Venturi valve, this means that the valve has to operate and control within its operating pressure in order for us to get control of that full operating flow range. So for the Venturi valve, there's two options available for that operating pressure range. You can have a low pressure Venturi valve, which requires at least 0.3 to 3 inches of pressure, or a medium pressure Venturi valve, which requires at least 0.6 to 3 inches in that sense. Now, these two valves are essentially factory calibrated at these ranges to ensure that you are still maintaining the accuracy out of these valves throughout the operating range. So, as mentioned earlier, in constant volume applications, we don't require any electronic components, be it a controller or actuator, to control airflow independent of those duct pressure fluctuations. But if we do want to be able to get an airflow feedback from that Venturi valve, then we're going to utilize the electronic flow or positional feedback from that potentiometer. So as you can see there, the electronic flow feedback That's giving us the ability to control and report airflow without the need of airflow measuring stations inside the airstream. That airflow feedback is provided from that precise potentiometer, which is outputting a signal proportional to the airflow. Now, that potentiometer is the sensor that helps report that positional feedback based off of the lever arm. So as you can see that potentiometer is mounted to measure the positional feedback of that lever arm. Again, this is all factory calibrated to ensure that factory certified airflow stations to ensure that positional feedback is accurate based off of measured flow going through the valve at the factory based off of third-party sensors. So the other option available for airflow metering valves is the operating pressure feedback. So as I mentioned earlier, these valves are going to be accurate to plus or minus 5% of flow when operating within the design pressure range. So what this means is the valves being selected should be able to measure and report the operating pressure for monitoring and alarming purposes. So the next design consideration we're going to cover is the contamination resistance. So with the Venturi valve technology, they're typically going to use low profile pressure ports. That's what's being used to measure the operating pressure at the high and exit ports, or the inlet and exit ports. So these low profile pressure ports give us protection from lint, dust, and other contaminants during normal operation of the air valve. And then additionally, since we can control airflow without the need of having a direct airflow measuring device inside the airstream, that also helps provide that this valve help minimize risk of contamination affecting the valve's ability to control. The next design consideration we're going to cover here again is the fan static reset. So as mentioned before, fan static reset is the static pressure set point is going to be reset based off of the zone requiring the most pressure. So to enable fan static reset, controls should be able to provide either of the following, being either to monitor zone damper position or provide some other indicator for need of static pressure. Well, for the Venturi valve, being able to monitor the actuator position doesn't actually tell us much about how much pressure the valve needs to operate. So in this case, we're going to monitor the valve through the operating pressure from the high and low pressure ports. So that's that other indicator for a need of static pressure. So buildings can monitor the valve operating pressure, reduce that fan static set point until the valve is operating closer to that minimum range on that valve operating pressure. Now, it is important to mention, not all Venturi valve manufacturers will provide some sort of static pressure monitoring as default. So it's always important just to double check with your vendor just to make sure that the option for static pressure feedback is either standard or it's an optional item that has to be specified. So the last design consideration we're going to cover here is the valve material options. So similar to the airflow metering style valves, depending on the project application and the expected chemical hazards, we should be selecting the valve material or finish to protect the operation of that valve. So ideally, we should be doing analysis to compare the hazard performance against the selected material. So with the Venturi valve style valves, you typically will have a bit more coated valve options available. So you're going to have your standard aluminum body valve, or we can utilize a phenolic coating class 1. So this again is an aluminum body valve coated in a phenolic coating that utilizes stainless steel internal hardware. A step above that is our phenolic coating class 2. So now instead we're still utilizing the phenolic coated aluminum body, but we're coating all of that stainless steel internal hardware in a PFA Teflon, ensuring that there's no exposed metal inside that airstream. And the final option available for the most corrosive type chemicals is the Kynar coating. So based again on the application intent, we should be able to select a valve material option based off of the project's hazards. So now that we understand intimately the available airflow control valves to consider for these projects, we can now finish off by covering, well, how can we design a project around these valves? So now that we understand the fundamentals, we can discuss what sort of airflow control sequencing is available. So the three options we're going to cover are constant volume applications, two position applications, and a fully variable volume application. So in constant volume applications, a Venturi valve can be ordered in a completely mechanically set constant volume application. This means the valve technology is coming with no controller, no actuator, and it's being mechanically locked to that set position for a single airflow set point. Now, typically, that set position can be field adjusted utilizing some knobs, but again, it'll typically come from the factory set for a single airflow set point. Now, if we wanted to design a high accuracy terminal unit to operate in a constant volume application, we will still have to have some sort of controller or actuator since we need those electronic components to give us that pressure independence. If we have a project where we want to design the air valves to operate in a two-position application, you can design a Venturi valve to come with a two-position actuator that has a relay for feedback. So again, this two-position actuator is just going to take a binary contact signal and drive the air valve from an occupied set point to an unoccupied set point. But if we do want to design a high accuracy terminal unit to operate in a two-position operation, again, we still need to provide it with the controller and the actuator, and the controller will control that valve between the two airflow set points. So the final operation here is going to be the variable volume application. So if we're designing for a fully variable volume application, we will still have to provide actuators and controllers for both the Venturi valve and the high accuracy terminal unit there. So with that, we can now get into the final section of this webinar, which is covering speed of response. So this is a really important thing to cover because now that we understand how the air valve technologies are going to operate, we need to understand it and ask the question, well, how quickly does these valves need to operate? Now, there's always going to be a little bit of a confusion when we talk about speed of response because speed of response can be defined to mean a number of different things. You can talk about speed of response directly correlating to the actuator speed. You can be referring to speed of response when there's a change in your duct static pressure. You can be referring to when there's a change introduced and how long does it take for that space to control again. We can be talking about the response to a control signal. So again, how fast do things react when we input a control signal response? And then finally, when we talk about speed of response, we could be talking about our fume hoods and the face velocity control loop and how fast does that need to operate. So what we're going to do is we're just going to define all of these speed of response definitions to ensure that when you're talking about your airflow control valves and you're understanding what type of speed of response is most important to your project. So the first definition for speed of response is the actuator speed. So this is essentially, well, how fast does our actuator stroke from fully open to fully closed? Well, typically you're going to see two types of actuator speeds utilized, either a standard speed actuator or a high speed actuator. So standard speed actuators will typically operate in about 90 seconds. These are typically going to be spaces that don't really have any fume hoods or equipment exhaust or essentially any sort of air device that requires fast actuations. So that typically falls under the healthcare realm, since typically in healthcare applications, we're not necessarily driving for absolute speed in our applications, but we're more looking for stability, and we're driving for stability in our control, stable operations. But when it comes to laboratory applications, they will often have the requirement for high speed response, since spaces will typically have those variable volume fume hoods. So if you are working an application with a laboratory, you're often going to see high-speed actuators specified all the way from the supply, exhaust, and fume hoods. But in a healthcare application, you may often see it utilize a standard speed actuator. So the next speed of response definition is going to be the speed of response to a change in duct static pressure changes. So if there's fluctuations in our duct, well, how fast does the air valve react to that? Well, for a high accuracy terminal unit, this response is still going to be very quick since we're still utilizing those electronic pressure independent devices, the controller and the actuator. and you do have the ability to tune that response. So you do have the ability to adjust some parameters to speed up that response if need be. But for a Venturi valve will always respond instantaneously to changes in duct pressure, since again it's mechanically pressure independent. So for a Venturi valve, out of the box, in application, will always operate instantaneously to those duct pressure fluctuations. But again, a high accuracy terminal unit can still be set up to operate very, very quickly and react and control to within a few seconds of changes to those duct static pressure. Uh, so the next speed of response definition here is going to be the response to after the speed of response of a space after a change is introduced. So here we're going to rely on the definition from ANSI and ISSP Z9.5. So for most operations, 10 seconds is often identified as an acceptable time to achieve the desired area pressurization, but a hazard evaluation should be conducted to determine the acceptable time. So what this means is if there is a change introduced, let's say a fume hood opens or closed, some doors open or closes, the room occupancy changes from occupied to unoccupied, it should take the room about 10 seconds to control back to the desired area pressurization. But of course, if you are working in an application that does have more severe hazards, we might need to make that a little bit quicker, maybe 8 seconds, 7 seconds, 5 seconds. So the next speed of response definition is the speed of response to a control signal, so that controlled response time. Essentially what this means is what is the amount of time for the controller to take to process a change in information and start to enact that change. So that again can be dialed in based off of the parameters available. So for the legacy or high accuracy terminal units, we may have the ability with control parameters to speed up the controlled response time or slow it down. But again, with Venturi valves, because there's no link or there isn't a feedback mechanism or feedback loop where the air valve has to continuously sample the airstream and adjust accordingly, the Venturi valve will often operate very, very quickly out of the box with minimal parameters that need to be adjusted, since again, the duct pressure fluctuations won't affect how the actual valve controls to the airflow set point changes. So the last speed of response definition we're going to cover here is the speed of response of a fume hood face velocity control loop. So again, here we're going to rely on ANSI and ASSP Z9.5. So what they state is the VAV control system must be capable of fast, accurate, and precise adjustment of flows without experiencing any major overshoot or undershoot greater than 10% of their steady state value. So clearly they're already outlining how the expected VAV control system should operate as an acceptable parameter. And then it further outlines a response time of less than 5 seconds after that fume hood sash movement is introduced, or a change in operating mode is considered acceptable. So again, now we're saying about 5 seconds is kind of our target time once we start to adjust the sash position or change the modes. So faster response times may improve hood containment, of course, but again, roughly following that 5 seconds as a worst case, that's the type of speed we're looking for in these control applications. Now, ASHRAE 110 also states very, very similarly and defines similar parameters that's acceptable for the fume hood face velocity control loop. So ASHRAE 110 also specifies how fast that hood should open when you're measuring the speed of response times. So it specifies the sash shall be open in a smooth motion at a velocity between 1 to 1.5 feet per second. And then it also outlines the time it takes from the start of the sash movement until the sash reaches the top, and the time it takes from the start of the sash movement until the face velocity reaches and maintains within 10%. That's what we're looking for. The design face velocity shall be recorded. So the benefit here again is the standards are very clear on what's acceptable performances for the fume hoods. And now we can start to apply an appropriate valve technology based off of the parameters that you guys are trying to meet for these critical space projects. So with that, we're going to go ahead and get into our summary. So to summarize this presentation, we spent a lot of time comparing the terminal unit, high accuracy terminal unit, and Venturi valve technologies. We discussed how both the terminal unit and high accuracy terminal unit are electronically pressure independent. They require that controller actuator to operate in a pressure independent fashion. But the Venturi valve with that internal cone spring assembly does operate mechanically pressure independent. We discussed the different airflow measurements. So again, terminal units will typically rely on velocity pressure, whereas a high accuracy terminal unit will utilize differential static pressure, but then the Venturi valve will rely on that positional feedback being measured by that high precision potentiometer. We talked about airflow feedback. Again, the terminal unit and high accuracy terminal unit directly measure airflow through a measured variable, versus the Venturi valve relies on that electronic feedback coming from the potentiometer, which is measuring the position that's correlated to the airflow the valve is going through. Now, both the high accuracy terminal unit and the Venturi valve do give us resistance to contamination based off of the inherent designs. We'll typically see higher turn down ratios available with high accuracy terminal units and Venturi valves. We'll typically see the minimum operating pressure for a high accuracy terminal unit operating a bit higher compared to the terminal unit at a 0.3. But again, that's 0.3 inches of static at the minimum operating pressure at the maximum airflow that the valve can do. So if we're looking for this valve to operate between the 40 to 60% range, a high accuracy terminal unit will often operate at 0.1 to 0.2 inches of static. Again, the Venturi valve, we're not worrying about minimum operating pressure for a Venturi valve. Instead, what we care about is the operating pressure. So that Venturi valve can be ordered to operate in a low or medium fashion. So the low version of the Venturi valve can operate between 0.33 inches, and then the medium pressure Venturi valve can operate between 0.6 to 3 inches. So the key item to note, again, with the operating pressure Venturi valve, as long as that valve's measuring the pressure across the valve and it's within this range, it will control accurately across the full range of that valve. Again, as mentioned, the high accuracy terminal unit and the Venturi valve doesn't require any straight duct. And then lastly, the material finishes available for high accuracy terminal unit and a Venturi valve will include either phenolic or stainless steel for the high accuracy terminal unit, or phenolic and a Kynar coating available for that Venturi valve. So to really highlight the key components we talked about today, we want to just focus again. We covered the contamination resistance available, we discussed turn down ratio, and we covered that minimum operating pressure and operating pressure for that Venturi valve.